Is the sound okay? Now these are on again, 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 these are on again. Yeah, this works? It's very loud. All right, so what I promised I would do now is tell you a little bit more fancy aspects of microlensing. And so what we're going to talk about is basically where the approximation that I've used breaks down. So what I described was the ideal perfect mathematical lensing by a point mass of a point source. And of course we know that neither the stars or points has a source nor as a lens. And so I'll talk a little bit about what this means in terms of finite source effect. So the fact that the source is not a point but is actually a little disk, a star, can have some effects in these very high magnification events. This is related to the idea of using it as a gravitational microscope to look at the structure of stars. And then I'll look at cases where you have extra information about the microlensing events, either because the lens or the source are, we can measure parallaxes from them. And then we'll make things more complicated. We'll talk about binary sources and then binary lenses, which is where you get the relation to possibly finding exoplanets. And then once we're done with all that, then we jump to the high redshift universe again and talk about microlensing of quasars, which can give some very interesting effects. Okay, so let's start with the finite source effects. When you do microlensing, certainly the macho survey and the kind of big projects I described before, the main interest is to find the mass of the objects doing the microlensing. That's what you really want to know. You want to know, are these things 10 to the 10 solar mass black holes? Are these things very faint 0.01 or 0.1 solar mass stars? Are they free floating planets? So the mass of the lenses is really the key parameter, and all the other things that come in there, like the distances, the speed with which they move through the halo, are kind of parameters that are a nuisance. You have to live with them, but you would like to get rid of them. So for a normal microlensing event, as I showed you before, what you can measure is the length, the duration of the event, and the duration is simply the time it takes to cross the Einstein radius. That sets the characteristics duration of this rise and fall in the brightness due to lensing. And if you plug in all the constants and the distances, you find that Einstein radius scales with the mass. Of course, there's a g and a c squared in there, but I'm forgetting these for now. It scales with the mass and with the combination of distances that you find in lensing, and of course we divide by the velocity to turn it into a time scale. Now the velocity is usually fairly well known in the sense that these are objects moving through the galaxy, and we know from dynamics of galaxies roughly how fast things have to move. If everything was standing still, the galaxy would collapse on itself. If everything is moving very fast, the galaxy would explode. And so there's a kind of mean velocity that you need to keep the galaxy in equilibrium, and that's typically 100, 200 kilometers per second. This is the kind of motions you need in the halo. So we have a good idea of the range for v, even if we cannot exactly tell event by event what this velocity is exactly, but we have a kind of statistical idea what it should be. Right? That's from dynamics. But what would be really interesting is to get also information on the geometry, on the distances. Once you have that, then you can turn your time scale that you measure, the duration of the event, into a good estimate of the mass, which is what you really want to know. So, one way in which you can get extra information about these distances is if you have a very high magnification event. So let me, I left my pens again. Okay. No pens. If you have a very high magnification event with a very sharp peak, let's say a magnification of over a factor of 10, that means you know you get very close to the center of the lens. And that means that, I'm sorry I don't have my pens now, but if you imagine the critical density, actually could someone go and fetch the pens from the office, because I'm going to need them. I forgot my pens. They're in the office. Could you get them? Thank you. This way I have 2 minutes without Jorge asking questions. This is really good. So basically what happens is that if if the source, so the source is a star. The star is a disk, it's not a point. If that source is of a comparable size to the Einstein radius of the lens, then the approximation we've been using is no good, because all the points of the star are not being lensed at the same time. The impact parameters, the betas, are very different for different parts of the star. It means that you never get the situation where all of the star is very highly magnified at the same time. And so effectively this means that you can have a very high magnification event, you can have the star come very close to the center, but nonetheless you will not see a very high peak in the light curve, because it's kind of smoothed out, because different parts of the star reach their peak magnification at different times. And if this happens, then you know something more about the distances. Then you know that the star, the angular size of the star on the sky, the radius of the star divided by the distance to the source, is comparable in size to the Einstein circle on the sky, so the Einstein radius divided by the distance to the lens. Now you typically know, you know how far your source is, and you also have a good idea what the radius of stars are, so this part is then roughly known, and that means you have an extra constraint on these distances. And that really helps to try to figure out the, to narrow down the possible range of masses that could have caused your microlensing event. Now this effect is most visible if the lens is very close to the source, because then the Einstein radius, if you remember the cigar, it's very thin, close to the observer, close to us. Then it broadens out halfway between us and the source, and then it gets narrower again as you get to the source. And so when you get close to the source, the Einstein radius gets smaller and can get down to the size of the star itself. So typically, if you see evidence for these finite source sizes by seeing that the peak of the curve doesn't quite fit, that it's a bit smoothed off, then you're pretty sure you have a lens that's very close to the source and not halfway between us and the source or close to us. So, and this is actually very important for interpreting the Macho survey, for example. They found a number of events, some with very high magnification, and in the beginning there was a big debate about whether there was a sign of this finite source effects or not. The point being that if they saw it, this finite source effect, then the lenses were very close to the source, and that means that they're very likely associated with the LMC and not with the halo of the galaxy ourselves. Thank you. So if you imagine the Einstein radius here, and you have a very high magnification event, so a star that tracks very close to the center, then if the star is very small, then you're going to get the light curves that I sketched before. You're going to get these very high symmetric peaks. But if the star is very large, this is the amplitude as a function of time. So if the star is very large, then you in principle would get the same thing, except this part of the star is not being magnified as much as this part. And so you will actually, more or less here, you will see pretty much the same thing, but when you get close to the center, you will find that the peak is a little bit rounder. It starts a little bit earlier, but it doesn't get quite as high. And so if you have very accurate measurements, and these are the brightest events, so these are the cases where you can make the best measurements, you can actually see the difference between these two different shapes of the light curve. And so in fact, one of the first bright events that the Macho collaboration found was a case where there was this rounding off of the top, which implied that the lens was in fact probably associated with the LMC and not with the halo in between at all. These are single events, but you have many, many data points, because as soon as the star starts to brighten, lots of telescopes start to follow it. Yes. And when we start to talk about planets, this will become even more important. So that's finite source effects, which complicate all the nice, simple analytic formula that I've given you before, to some extent. Second effect is microlensing parallax. In the classic microlensing case, you have us sitting here still. You have a lens somewhere in the foreground. It's passing through, or you can think of the lens as standing still and the source passing through the sky, and the source is passing through this magnification pattern that's created by the lens. So here you can simply read off as a function of time what the magnification is, and you make one of these transit curves. Now, of course, in the end, in reality, we aren't standing still. We're moving on the Earth around the Sun, and our telescopes are not on the Sun, but our telescopes are on the Earth. So they're moving once a year. They're making a little circle through space. And that's what we call parallax. That's one way to measure distances in astronomy. And also it affects the microlensing, because if you imagine that the Earth has moved up by 1 astronomical unit this way, that means that we're actually looking effectively at a different part of the magnification pattern with our source. It's like we're moving the lens has a parallax that's moving in front of the source. And so this means that our path through the magnification pattern is no longer straight, but it has a wiggle in it. And that means that we also get the slightly altered transit curve. You will find some sort of perturbation around this transit curve, which I'm now drawing very exaggeratedly, with a period of 1 year, because it's driven by our motion of 1 year up and down around the Sun. And there's examples. Let's imagine that you can measure this thing. If you can measure it, what you see is effectively in the image, in the source plane, effectively you're measuring this combination of the distances. You're measuring our parallax multiplied out to the scale in the image plane. So that's 1 astronomical unit times DDS over DD. That's what you can constrain if you can detect and measure the amplitude of this parallax effect. And that you can compare with the Einstein radius size, again projected to the image plane, which is the Einstein radius times ds over dd. So it's the ratio of these two things that you can determine if you can measure one of these parallax events. So that's this quantity here, RE ds over dds. And so you see that once again this gives you a way to get an extra constraint on the distance ratios, and therefore a way to break this uncertainty about what the mass of the lens is. So the event duration gives you RE over V. That's what I showed you earlier today. This parallax gives you this combination. If you take the ratio, then you end up with something which is completely independent of the Einstein radius, and it purely tells you about the distance ratios, about the geometry. So it tells you something about where the lens is along the line of sight. And if you know something about the typical velocities, that means you can work out something about the probability of where the lens is. And so there's all kinds of statistical techniques to incorporate all this information in an optimal way. This really just illustrates the fact that it adds extra information. Tell me.
Okay, could you go back to the previous slide? Okay.
Yeah.
Okay. What does this this effect that you said is useful to measure or to constrain the? Could you repeat me that part? You said that this effect is with this effect you can constrain the distance to the source. In
yes.
Which way, yes?
Because so normally you forget this parallax, then you would measure a straight line path through this magnification pattern. This magnification pattern we've calculated for the point mass lens. But instead, because of the parallax, we will make a kind of zigzag through here. We will have an oscillation. And so you can measure this as a deviation from the best fit microlensing curve. And the amplitude of that basically tells you how large the excursions of the star about the mean path are. And the amplitude of that effect scales with this quantity here.
But the amplitude measure in magnification, you mean?
Yes, so you measure, yes, indeed.
In magnification.
You do it through the magnification. So here's an example. This is a real event, very well measured, where this parallax is very clearly visible. So here is a microlensing event, high magnification, long duration, which is what you need because this parallax takes a year. So if you have an event that lasts 2 days, you will never see it. You really need to sample a large part of a full parallax cycle. And this one here is, well, it's only 2 months, in fact. It's not bad. Okay. And what you can see is that the best fit is the dotted line, the best fit normal microlensing curve, and you see that systematically the star is either too bright or too faint. And here at the top you see the residuals magnified out. And you see that here it spends a long time being too faint, which means it's a little bit too far from the center of the lens. And then here it's too bright, it gets too close to the lens, and then you get these funny oscillations. This is exactly what you get if you take a path through, the straight line path through the magnification pattern, and you add this oscillation on top. And so this was just a zoom in of the peak, in fact. So the peak is very short, but all these residuals happen over many hundreds of days. In fact, the whole thing is more than 1,000 days length, so this is a 3-year event. That's why you can see many oscillations. And again, this is most visible in events which have a very high peak magnification just because the observations are that much more accurate. Okay, then we have another effect which some funny guy decided to call Xalarap, which is parallax spelled backwards. And it's because it's the inverse effect of parallax. So now it's not an effect which is due to our motion in an orbit, but it's an effect due to the motion of the source. This is the case where the source is a binary star moving in an ellipse as well as tracing through the magnification pattern. So then it's actually similar to parallax in its effect. You also have the source moving not in a straight line through the magnification pattern, but with some extra oscillations. The difference is that the period here is now no longer 1 year. It can be anything. It's just the period of the binary star. It has nothing to do with our motion around the sun. But apart from that, it's actually very, very comparable. The advantage is that in binary stars, if you can measure the radial velocity of the binary star, you can actually determine the size of the orbit. Right? If you know how fast the orbit is moving and how long it takes to complete one orbit, you know the size of this orbit in kilometers. And it's another way of turning this relative scale, this projected Einstein scale, into a physical scale on the sky. And therefore, again, breaking this degeneracy between the distances and the masses that we have in the microlensing. So if you study the binary star well, you know the size of this orbit. That tells you the size of the excursion, and you're in business. And there's a few examples like this too. Here's one. Same thing, you have a pretty decent fit to a standard classic microlensing curve, but if you look carefully, you see there are systematic deviations, and these systematic deviations have a period, which in this case is much shorter than the previous example because it's the period of the binary star and not the period of our orbit around the sun. Okay. And so this is another case where that gave enough information to decide that the distance was probably very large and that the lens that was causing this microlensing was probably not halfway between us and the Magellanic Clouds, but was also in the Magellanic Clouds itself. And it's actually kind of the story of much of the microlensing towards the Magellanic Cloud. All the events where you could say something extra because of these extra effects almost always made it much more likely that the lens was not in the halo, but was a faint star in the halo of the LMC instead. Okay. So much for binary sources and us having a parallax effect. Now let's get more complicated and talk about binary lenses. And binary lenses is very different because now you can have very complex optical effects. You can change the caustics, you can change the critical curves, and you can, in certain conditions, generate very short periods of really huge magnification from the fact that you have a binary. So we'll go through all this. This is a kind of a summary of what we're going to be discussing here. But the largest effects you get so imagine that you have a single star, single lens, Einstein circle around it, and imagine that it has a little planet. If that planet was sitting here or sitting here, it wouldn't affect the lensing of a background star very much at all. But if the planet is sitting right on the Einstein circle, right on the critical curve, then that's going to significantly perturb the critical curve and do funny things in the caustic plane, which is where the source moves. And if the source happens to move close to this planet, then this is where you can get all the wacky stuff, all the strange effects. So very small perturbation, you can really get very small planetary masses, make big changes to the Fermat surface, and therefore big changes to the images that you see. And what I'll show you is what kind of caustics you get in the source plane, which is the way to visualize the effects that you get this way. And so this has turned out to be a very powerful way of detecting exoplanets. And we'll talk a little bit about what's been learned with that. It's interesting because it probes the orbital range further out than where radial velocities typically get. Right? If you look for planets, then there are basically three ways of doing it. You can do radial velocities to see the star move back and forth. That's most sensitive to massive planets close in, because those are the ones that are able to make the star significantly oscillate. Although these techniques are getting better and better and better, and so you can see faint, lighter and larger orbit stars ever more. So that's the small radius limit, and then the large radius limit is astrometry, where you look for very wide orbits where the star is moving and being pulled. Those are very slow, very long orbits, so it takes a long time to get good information, and the exoplanets are kind of in between this regime. So it's turned out to be very useful astrophysically. The sad thing about exoplanets is that you can detect them, but you cannot see them. And moreover, you're never going to see them again. Because microlensing is a single event. It just happens to be this one star passing in front of a background star. And once the event is over, the event is over. And also the planet is over. So you will know that there is a star there which has a planet. You probably know more or less what the distance is, because you can do all these microlensing analyses. But that's really all you know. So you cannot, it's not a planet you will ever study. It's always a planet that's going to be very far away, because microlensing doesn't happen for close by lenses. So it's a good statistical tool, but it's not a way to study exoplanets per se.
Could you speak slower?
Pardon?
Could you speak slower?
I can try. Thank you.
You are speaking very fast.
Ask me again if I have to.
Yes, I think so.
Okay. I have the feeling I have a lot of material, that's why I'm trying to speed up, which is a bad idea. Okay. So these microlensing planets are very exciting, but they're not things we can study directly. Also, usually you cannot even see the host star, the parent star of the planet, because that's sitting right in front of a bright distant source that's being lensed. So usually you don't even see the star. You simply see that there's some mass concentration there that's causing lensing. And as I said, it's more likely to occur for lenses which are quite far away, which again makes it very hard to study the planets directly.
Just one question. You point out that, of course, you cannot come back to the planet once you have detected such a planet. So basically, what you're doing with detecting planets in that way is you're adding a bit of notion to the statistics
Exactly.
of planets elsewhere. Can you give me a feel for the numbers involved? Have we got 30, 300 of these cases?
I think there are dozens of that order of microlensing planets detected. But I'm not sure. I haven't followed this lately, so in the last
I remember a number obtained by this kind of surveys, and the number is that according to OGLE, this OGLE surveys that there is 1.6 planet per star in the Milky Way. So it's a lot sure. Of that. Yes.
But I don't know on how many planets that's based. I mean, obviously that's an extrapolation because they haven't looked at every star in the Milky Way. But I don't know if this is based on a sample of 100 microlenses or 10 or 1,000. I don't know the answer.
Okay. And the other question is, it's strange that you can see the source, but not the lens, since they are stars. So you have to expect that the source will be much less brighter than the lens. So actually, these measurements should be biased to low mass stars or not?
No, because usually the source stars that you can I mean, you want to be able to see the star also when it's not lensed, right? When it's not at the peak of the magnification. So usually the source stars are relatively bright, and people sometimes use clump giants, for example, or turn-off stars, but certainly not M stars because you cannot see them.
Of course.
So they're much fainter, also in apparent magnitude, than the star doing the lensing.
Okay.
Yes?
See you later.
My question is, what is the better method for detect exoplanets? This of the transit method of the velocity, radial velocity of the planets with the host star?
They're very complementary. So the radial velocity is very good for planets close to the star, and also for nearby stars. The transits are very good for low mass stars, and of course there I think transits are again better for short periods because it gives you a better chance to actually see a transit. And the microlenses are kind of a regime in between. So it's not that one is better than the other, but in the end they're different aspects of the same universe, of course. So you can put all the information together.
Useful together.
It's useful to combine, exactly.
Thank you.
And so this is really good because it's a very nice statistical method that comes for free out of some of these other microlensing studies. Okay, binary lenses. So what I'm going to show you now is a sequence of critical curves and caustics for the case where you have two masses, two lenses of the same mass that I'm bringing closer and closer and closer together. So here we start with the two lenses separated by 1.2 Einstein radii, or twice 1.2 actually. So this lens is a plus 1.2, this lens is a minus 1.2. If there were only one lens, then you would have a critical curve which is the size of the Einstein radius here. And because the two lens potentials add up, if you think of this in terms of the Fermat potential, you're generating extra bumps. You're generating a saddle point here in the middle, for example, and the corresponding structure in the source plane are these caustics, and you see that you end up with these very strange, pointy structures that originate. And this is all because you're folding the image plane in a very complicated way back into the source plane. And these caustics here, the edges of these caustics are where these folds are happening, you know, where you're actually folding the sky back on itself. So that's why when you take a source and you cross from outside to inside a caustic, you suddenly cut the image plane twice more, so you end up with two more images than out here. So out here you have a single image. When you get in here, you create two more. And when you're on one of these caustics, you have at least one part of the source that's magnified infinitely, so you get a very strong brightening of the source. And when you go to the cusp here, you're actually merging three images or creating three images simultaneously, so you get even stronger magnifications. Also, when you pass very close to a cusp but not quite through it, then you're magnifying one of your images. You're not creating new ones, but you're certainly increasing the magnification a lot. Later I will show you maps of magnification in the source plane which make this clearer. But first let's go through the sequence. So let's move these two lenses closer together. This is where they're separated by exactly plus or minus 1 Einstein radius. So this is a sort of symmetric point. You see that these two caustics, which were separate in the previous case, have now just touched. They just merge. And when we go even further, you see that the structure now starts to stretch in that direction. So it goes from here, and then it stretches that way. So this is now even closer. They're separated by plus or minus half an Einstein radius, and now you see this beautiful six-fold caustic in the source plane. This is another critical case where the separation is 1 over the square root of 8. Then again you see you're about to split off some parts of the caustic into separate pieces. And so when you go to closer, that's what you get. You get the central caustic here. So this is now beginning to look a little bit like an elliptical mass distribution like the one that we talked about in the beginning, right? It still has 2-point masses in it, but overall the critical curve is now almost a nice ellipse. And the central caustic is actually also quite similar to the central caustic that we found for a galaxy. But you still have these two other things which are associated with the fact that we have 2-point masses in there. Let's see, do I have one more? No. And so what happens with these caustics, so before in strong lensing we were always talking about the image plane and the critical curves, because that's what you can see on the sky, the image plane. And you could see where the critical curves were, you could see where the very distorted images were, you could see the high magnification events. In microlensing, all this is completely below the resolution scale. In microlensing, you cannot see this. In microlensing, all you see is this brightening. And so to visualize this, it's better to go to the source plane and think about what's happening when the source is moving through one of these special regions where there are caustics. So here, for example, is a calculation where we've taken the caustics from this case here, where the separation is exactly 1 Einstein radius from here to here, right, plus or minus a half. And we've calculated what happens to the brightness of a star that tracks through the source plane along various paths. There's 5 cases in 5 different colors. And you see, let's start with the blue one. The blue one never quite goes through the caustic, so it never generates, it never spontaneously creates new images, so there should be no discontinuity. It's a smooth change, and that's what you see here. You get this kind of double bump structure. This bump here is when you're near this caustic peak here, and this sharper bump here is when you're close to this part here. There's a lot of high magnification on the caustics. Right? Formally, remember, on the caustic, the magnification of any point that's on the caustic is infinite. But because you've got a little disk, not all the points are being magnified infinitely at the same time, and so that's why the curves are rounded off a little bit. And then when you track through the various other cases, you see that you get a kind of continuum of change. This light blue one goes right through this caustic, so here you get a sharp event, and then it spends a lot of time here, again with a lot of high magnification. The green one, same thing, you get much sharper changes in the brightness because it's crossing one of these caustics head-on. Almost the whole star is being suddenly extra magnified or extra imaged simultaneously, and so on and so forth. So you see there's a very rich phenomenology, a very rich family of possible light curves that you can get. Of course, you can also cut through this in many other angles and get many other light curves. And so what you can do if you find a light curve like this, which looks very strange, is to try to figure out exactly how this star should have tracked across the source plane to reproduce these things. And so there's tremendous amount of information in it, simply because these features are so very sharp and so very bright. Right. So this is, remember, this is a case, this is not a star with a planet, this is a binary star of two equal masses. But you will see later that even when one of the lenses is much heavier than the other, even then we can get, under certain conditions, these very, very bright events. Was there a question?
A lot.
A lot of questions.
A lot, but okay.
So,
for example, I still have the question that why do you abandon the critical curves and go to the caustic? Why do you use the caustic and not the critical curve?
Because the critical curve, if you have that, you could compare, supposing we could take an extremely sharp image, then we would see the image plane, and we would actually see the multiple images caused by the microlensing. We would see the extra images caused by the binary, etc. But we don't have any of that information because we don't have an image that's sharp enough. It's all happening on much too small a scale. So instead, all we know is that when a star hits a caustic in the source plane, something is going to happen, something spectacular is going to happen to the light curve. Right? In this green case, for example, it's suddenly, this is the effect of two new images being created and being very bright.
But you still can predict the same thing using the critical curve.
You can. You could, at any of these, at this point, for example, you could calculate what the images actually look like. And they look like a mess.
Okay, it's just a matter of convenience.
Here, we have the critical curves here, right?
Yes.
So you see the critical curves can be very complicated, and so you will generate very complicated images when you come close to the caustics in the source plane. It's nothing to stop you. It's just not useful because you cannot compare it to the observations.
If you are doing microlensing, you have to understand better how caustics are calculated.
Indeed, yeah.
Have to be here.
In the case of those critical curves where it folds when it folds in itself, and the later one where the masses were closer, I saw two small circles. Yeah. How does the image behave around those circles and around those points of craziness in the critical curve?
Here, actually, I'm not sure what this means. I think probably it's I think I do know what this means. So the pluses and the minuses say whether the magnification is positive or negative. So it's either positive parity or negative parity in the lens map. And so when you cross a critical curve, you switch parity. And so what happens when you move from this kind of critical case to moving the lenses even closer is that these two little loops split off into two separate things here. And that means that you're able to generate extra images. If you cross one of these caustics, I don't know which one now, I guess C2. If you cross C2, you generate new images near this critical curve here. So there's actually a lot of description in the chapter on microlensing on this. So if you're interested in these aspects, then take a look at the book. Okay, now because we have to understand to the source plane, the caustics, it's important to try to visualize not just where the caustics are, but also where the magnification, what the magnification looks like in the source plane. Because as we saw here, the magnification certainly does something spectacular when you're on a caustic, but also in between, far away, here and here, you also see effects. So the magnification pattern on that field is certainly much more complicated than just given by the caustics. So the way to visualize this, and this is something if you like experiments with a computer, this is an easy thing to do. To visualize magnification is you simply take the image plane, cover it uniformly with points, and map those back to the source plane through the lens equation, right? Which is a very easy thing to do, and you can do this for as complicated a lensing potential as you like. I'm going to show you the case just for 2-point masses. Because what that shows you is that it shows you where in the source plane lots of points come from the same part of the image plane. And so that means that those tiny parts of the source plane end up very big in the image plane. In other words, they're being magnified very greatly. So let me give you an example. This is for a single point mass lens. So I've just taken a rectangular grid, a very fine rectangular grid, and instead of plotting the grid, I've plotted all the lines in the source plane, so mapped through the point mass lens equation. And what you see is that the grid is no longer uniform, but that there's a lot of concentration right in the center here. And this is what we should have expected. This is the source plane. The caustic in the source plane for a point lens is just the origin. It's just the middle. Because it's only in the middle that you have the infinite magnification and the images on the critical curve for a point mass. Right? So you see a lot of the image plane comes out of this very small part of the source plane. In other words, this small part of the source plane generates a large number of images. And we can zoom in a little bit, and some of this cross is an artifact of the fact that I'm using a grid and not just random points, but you can do this with random points too. And as you zoom in, you see really that all the strongest magnification is right in the middle, but also around there, around the point, the magnification is higher, the density is higher. Now let's add a point mass. So now I'm doing the same thing, but now I'm making my lens model a bit more complicated. Here's my point mass lens, and I'm adding a second point mass with the mass 10% of the central one. So I'm giving this guy a little satellite, and I'm putting the satellite right on the Einstein radius because I know that that's where the interesting effects happen. And when you do this mapping back, you see that now not everything concentrates in the middle, but you start to see this complicated caustic pattern that we were getting before. And the fact that you get these sharp edges, this is exactly the edges of the folding of the image plane into the source plane that causes all the strong lensing features. So I think we can zoom in a little bit on this. This is the same case, but just zooming in. And you see that this pattern is actually very large. This is in the source plane now. This goes out to half of the Einstein radius. So this is actually a large part of the source plane which is affected, where you will get very high magnification, very high density in this diagram if you put a source there. Right? So if you put a source here, this source gets mapped back from a lot of image points, so this source is going to be magnified very strongly. And what you see here also is what we saw before in the light curves, that the cusps have a peak, but also around the cusp there's a lot of points, so there's a lot of high density, a lot of high magnification. So coming near a cusp is always a good way to generate a bump in a light curve, even if you do not actually cross it itself.
Good. Again, what you are doing here is mapping the points in the image plane to the source plane, right?
Yeah.
So this is a way this is also a way to numerically plot the caustics, right? Actually, the caustic will
you see the
will
caustics
arise
like this.
Yes.
You get them visually. It's not a good way to get a mathematical formula or a trace of the envelope, but you see where they are. You visualize them very quickly. This way. Actually, getting the caustics mathematically is kind of a pain sometimes. But yeah, you just take a grid here, and then you, for every point on this grid, or for every point on each of these lines, you work out where in the source plane it would have been. So it's a 5-line computer program. It's really, and it's a lot of fun when you can think of all kinds of crazy lenses and you will discover a very strange thing. So, Okay, so this is a 10% point mass lens. Let's make it 1%. And you see, even if it's 1%, if you put it in the right place, right on the Einstein radius, you can actually generate a large caustic in the source plane. So if you're going to move this point mass away from the lens, and you will this will very quickly shrink. But this shows that it's certainly possible to have a fairly large effect. So any microlensing event which comes very close to the center, so which will have a very high amplification, if it happens to come near this point mass, will also give you a very strong extra features because of this caustic. And here again, I've made the mass even smaller. It's now 0.3%. And still you see that there's a strong effect. Even 0.1%, and it becomes a bit hard to see. So here's a different visualization of the same thing. I've gone back to the 10%. And now I'm going to show you a little movie which shows what happens to the caustics when this source, when I move the planet. So I'm always having the source in the same place. Yes, the source is always behind here, and I'm moving the planet around. And let's see where the caustics move in this case. So you see, this is the case we started with. When you get inside the Einstein radius, you split off two satellites in this direction, and when you go outside the Einstein radius, you split off a satellite in this direction. And again, you know, if you're a genius in multidimensional geometry, maybe you can visualize this and predict this. I find this simply something to be experimental with, and to make movies like this and calculations like this. And the point is that this will always show you exactly where you would have to come with a source to give you an interesting microlensing curve. Okay, and so the point is that when you have a point lens like this with a little satellite, so a star with a planet acting as a lens, if you have the right track of the source close to one of these extra caustics, then your light curve is going to be perturbed or very, very strongly changed. So here's one example. This, I think, is one of the most spectacular cases of a planet. This is an event that was brightening very fast. It started off at 19th magnitude and was on track to go to 14th or so. So that's a brightening of almost a factor of 100. Very, very strong. Really almost a bullseye in terms of the source going behind the lens. And it happens that this lens had a little planet. And so somewhere in the source plane, you have this caustic. This is a case where the caustic is like this, and it moved. The track of the source was very, very close to the end of this caustic. And that gave rise to this very intricate variation. And the amazing thing is, if you look at the data points and the curve, they agree phenomenally well. So this is a very complicated variation of a very bright star, so it's very well measured. And with a model which, you know, in the end only has a few parameters, right? It has the mass of the satellite, the direction with which the star comes, how close it comes to the center, maybe a few other parameters. And with that, you're able to reproduce all this very rich structure in this light curve to phenomenal accuracy. So this really is, in a sense, it's pure, simple geometry, but turned into a very complicated phenomenon. And here is the same thing in the image plane, I think. Is it? No, this is the source plane again. So this is the full light curve here. This is a different event. This is a different event. In this event, you suddenly have you see there's a caustic crossing which generates a very sharp spike. Then you go back through the caustic, you lose it again, another one. So I don't think this has the track of the source through the source plane here. But this is a magnification of this part here, and again, there's some data points on here which you can hardly see, and they agree phenomenally well with the model. Ah, no, here, it's a movie, that's why. So this is a movie which shows all the various events, all the various important times in this event. So
the little dots were the images. The little dots are the images of the source.
So this here, this is in the source plane. So this is the source tracking across the caustic here.
Oh my God.
These purple things are the extra images that are created and destroyed. You see, here's a pair coming, here's a pair going. And when that happens is when the spikes happen in the light curve. And here also in the center you see all the images. So the purple ones are the images. You see a lot of extra images generated by this fold in the critical curve that the planet has generated. So it's really amazing, this, I think. And there's even cases of a two-planet system. Always need more. So this is a case with a really very weird light curve, and in the end they were able to solve this by adding a second planet to the model, which gets very complicated, and I'm amazed that they were able to do this. Actually, one other complication with these kind of models is that if you have an event where the duration is very long, then while the source is tracking across your Einstein radius, the planet is actually moving. So this makes it even more complicated, even more things to think about. Right? And certainly if you have a case where there are several caustics, then the caustics may actually have rotated because they depend on where the planet is between when the first and the second contact appear. So there was some discussion whether it was this system or a different one. There was some discussion whether you needed two planets or just to take into account the fact that the planet was moving around the lens. So. Anyway.
I was wondering if you can predict, if you can predict where the source will be in a while. I mean, in a few years. Of course, the movement, the apparent movement of the source is a combination of the movement of the lens and the source itself.
Yeah, it's really the difference of the proper motions on the sky.
Okay, yes.
So yes, you know that in the end they will separate if you wait long enough.
Yes.
You will be able to see them both. And there are some cases, in fact, where people have waited long enough and they've seen this little faint lens.
But haven't they tried to use some kind of dynamical model of the galaxy to predict a second? No. Okay, no.
No, you cannot say when you're going to hit another star because you need to know it to milli-arcsecond accuracy.
Okay.
Where you're going to come.
Right.
Maybe. Yeah. Okay, and so the way to do this, to the subject, to find these microlensing planets is, of course, monitoring. You have to observe lots of stars all the time, look for the ones that are causing the microlensing, and then catch them early enough and keep a flag with the ones that are going to be very, very bright. And the ones that are going to be very bright are the ones where all these phenomena can happen. And so typically what happens is that there's a number of survey programs. At the moment, OGLE, I think, is the most active one. And they generate alerts all the time. So whenever they see a microlensing event that looks like it's going to get really bright, they send out the coordinates and they tell everyone with a telescope who wants to keep monitoring this star as often as possible so you can get these very high resolution light curves and even try to find these sharp changes in the magnification. And so this is actually something which is excellent science for small telescopes and even amateur groups. So having lots of people involved really helps to get coverage around the clock because there's always some part of the planet that can see the microlensing event. Sometimes it's cloudy over one observatory but clear over the other one, etc. So many of these light curves I showed you had combinations of many different observations, many different observatories put together into a single data set. Okay. So to summarize, the microlensing by exoplanets gives you planets which are complementary to the other techniques, radio velocities, astrometric searches. You typically find planets around the Einstein radius. That's where all these phenomena happen, and that's a radius that's usually significantly further out than probed in other ways. And if the alignment is right, you can actually see very low masses. So people have been able to see Neptune mass microlensing planets, for example. And as we discussed before, they have certain disadvantages because once you see them, you better look carefully because you're never going to see them again. Okay, then the final topic. So any questions on exoplanets before I switch to quasars? No? Okay, so then this is a very short section on on what's called high optical depth microlensing. So the regime where microlensing is not extremely rare, like probability of 10 to the minus 6, 10 to the minus 7, but more like 1/10 or higher.
I was wondering if they have detected substellar objects using these substellar objects using these surveys, this microlensing survey. I mean,
so you don't mean as planets, but just as free-floating signals?
Yes, free-floating planets, for example. Did you know?
Actually, I'm not sure. I think it would be very difficult to prove that you had a substellar object, because it's so difficult to determine the mass. You only measure this combination of the mass with the speed and the distances, that usually there's always a way out to change the distances or to change the velocity. So usually you don't have enough information to... All right. So microlensing, I said, happens in a Milky Way, but in fact it also happens to very high distance quasars. So let's consider the case of a distant quasar behind a galaxy. The galaxy acts as a lens, and so the usual diagram, here's the galaxy, here's the quasar, here are we, and we're getting certain light paths from the quasar to us. And suppose that one of these light paths comes quite close to the galaxy and actually passes through a part of the galaxy where there's a lot of stars. So that means that this part of the galaxy, actually, this lens is not smooth, but this lens consists of lots and lots and lots of point particles, lots and lots of delta functions. So this is what we call a grainy lens. Has lots of substructure. And that means we can get a phenomenon just like microlensing happening here. So the optical depth to microlensing that we calculated before, this integral that we did in the first session today, it's the integral of the Einstein radius squared, right? It's the integral over the cigar that I showed you. If you now imagine that we have this cigar plotted here around this lens, then actually all the mass is not here or here, but all the mass is pretty much at the same distance, namely the distance of the quasar. And so this integral collapses into just a single, it's zero, except this row is zero except at just one single z value, and so you end up collapsing the lens and getting the surface mass density at that redshift, or at that distance. And if you look at all the other constants in front of it, you see that it's actually exactly the combination of surface mass density divided by the critical density for lensing. So you end up, as if by magic, just with kappa, with the dimensionless surface mass density as being the optical depth to microlensing. So if here, supposing that this part of the galaxy had a kappa of 0.12, that the surface density here was 12% of the critical density, then you immediately know that there's a 12% chance of this distant quasar to be microlensed as well. 12% of the sky is covered by Einstein disks for microlensing. And actually this is kind of obvious because the mean kappa is 1 inside the Einstein radius, and so kappa tells you the fraction of the sky. If you imagine covering the sky with little Einstein circles, then tau tells you the fraction of the sky that you cover to get the total surface mass density that you get. And so this is going to cause lots of multiple imaging of quasars. So the single image of the quasar, because of microlensing, is very often going to break up into multiple images. And so what I wanted to end with today is show you some simulations of how that happens. And so this is a much more grainy lensing potential than just 1 or 1 plus a little bit. Lenses, this is really lots. Potential.
Okay, this is the effect for one source. Okay. Yes, okay. Yes, but what happened with diffuse source? If you have a microwave background radiation or a okay,